start our project on non-standard probabilities based on paraconsistent logics. In this talk, I intend to show, without technical details, I try to give some intuitions about the consistent probability, and I will give an example at the end of the presentation. Okay, I structured the presentation in introduction, then I talk a little bit about logics of formal consistency, that is a family of consistent logics. And I will discuss in a little bit more detail about paraconsistent probability theory, and is an example. Okay. Logic and probability are essential tools in the formal study of reasoning employed in various fields, including philosophy, artificial intelligence, cognitive science, and mathematics, that can be integrated in two distinct ways. The first approach, we extended the language of the logic with new operator, and this operator can express the notion of probability inside the system as logic. And the second approach, we provide the probabilistic semantics for two logic systems. We change in a consequence relation, we change the evaluation by a probabilistic entailment. And our approach follows the second approach here. Okay. Let's start with classical probability. Kolmogorov gives three axioms to express the definition of probability. In his account, we work on a set. Okay, we think in terms of sets. Each event receives probability in the interval 0, 1. The sample space, the set omega, receives probability 1, the maximum. And we have the finite additivity. We can extend this third axiom, but for my presentation, this format is enough to discuss. Of course, we can derive from the axioms that, for example, probability of the empty set is 0. Okay, and in classical probability, we have a conditional probability. Okay, defined by the Bayesian form, and this probability are connected in a certain way with logic, because we say probability of A given B is like the same probability of B implies A. We have lots of problems with this connection, but this is not important to me in this talk today, but I know it. But I'm interested in this particular case. Probability of A give the complement of A is 0, because the intersection between A and its complement is an empty set. Okay, but we can ask: is it really necessary that probability of A and the complement is 0? Of course, if I think in terms of sets, like Kolmogorov did, it's completely right, because in classical probability theory, we connect the theory with classical logic. Okay, but If I think in terms of information, for example, in this case, if the complement is a vague information or incoherent or excessive information, which is the reason to take probability of the A intersection if the complement is zero. That is the point we start, okay? Because we have situations where I have logics that allows that the contradiction is not a real problem in the system. Okay? So to deal with this kind of situation, a new notion of probability theory is justifiable. And to do this, we work not in terms of sets like Kolmogorov, but in terms of sentence. And to make this distinction, I will use capital letters for represent events, like Kolmogorov, and Greek letters to represent sentences. And I will make the connection between logic and probability theory, like Carnap's work and Popper's work. And this now, let's talk about paraconsistent logic. How I can distinguish classical logic from paraconsistent logic? If I pay attention on the negation, we can see a difference. In classical logic, we have that the negation is explosive in the sense that from a pair of contradiction, we derive beta for every beta, which means the system is trivialize the system. Contradiction, trivialize the system. Paraconsistent logic does not agree with this principle. We accept this other principle. From a contradiction, we do not derive beta for some beta, which means that the contradiction does not trivialize the system. Okay, with this distinction, we can separate concepts. Concepts that in classical logic are equivalent, in paraconsistent logic, this is not necessary. For example, the notion of consistency and non-contradiction. In classical logic, these are equivalent, but in paraconsistent logic, not necessarily is equivalent. For example, we have two situations to understand the difference. Contradictory information about bank balances is not tolerable, while a contradictory information about weather forecast is tolerable. And then, to make such a distinction in the system, we use a new operator that we represent by a white ball, which represents the consistency of the formula or the sentence. And with this new operator being added to the language of the logic, we develop a family of logics of formal consistent, a family of paraconsistent logics, where notions like consistency and no contradiction can be different. And then I will make a control of negation and recover this equivalence in the system. And in this approach, we can derive or recover the classical logic, taking into consideration that all sentences or all contexts are considered consistent. For example, in logic of formal consistency, we adopt this principle. principle of gentle exclusion, which means if a contradiction occurs in that forms that I accept that are consistent or that has the classical behavior, then the system will be trivialized. If not, contradiction is not the truth. This is the philosophical principle that we paraconsistent logic follows. So we have a family of paraconsistent logics, and in this organization I separate by kind of semantics that we can characterize the paraconsistent system. The first one, this group, starting from a positive fragment of propositional calculus.
By characterizable by finite matrices, do you mean logical operators are definable by truth tables?
Yes.
That's what you mean, okay.
Yeah, but I'm talking just for the paraconsistent logic, of course. And here we have are characterized by matrices, okay? And then, conform I add new axioms to the system, I get close to classical propositional logic. In the limits, when all sentences are considered to be consistent, I have classical proposition. The second group is this one, that is characterized by three-valued logics. They start from the logic of paradox, LP of Priest, and then we have the logic of formally consistent LFI1, and we can get classical propositional logic. And the third group, not first degree intent logic, but this logic here is characterized by non-deterministic semantics. Okay? This is the logic of evidence and truth. Last week we talked about this logic. Okay? In our work, we developed paraconsistent probability theory with three different logics. Okay? Now I will explain the idea of to make the connection between this logic and this probability. First, I will see about each logic. LFI1 was proposed to treat with contradictory information inside the evolutionary database, and it is maximum relative to a conservative extension of PC and validate most of the Morgan's law. The second system is one of the weakest systems of the hierarchy, where contradictoriness and inconsistency are identified. This system is very, very close to positional logic. This was the first system that we worked for this reason, okay? And the third one, logic of evidence and truth, is an extension of the four-valued logic, first degree intent, and it is a logic of informal consistency and indeterminateness, in which the operator of consistency recovers classical logic for proposition in its scope. In this logic, the notion of evidence is a notion weaker than truth, in the sense that there may be evidence for proposition alpha, even if alpha is not true. Okay? This is the system. Now, let me make a representation of the connection between the classical analysis, classical probability with logic, and paraconsistent probability. In homogorgic definition of probability based on sets, okay? The classical definition, we have a connection or an intuition. We can understand this approach by using finite activity or other properties. We can think in terms of Boolean algebra. There are very close connection with this. But this, in this setting, probability is used by engineers, for example, when we apply statistics. But I can make an analysis of the theory by work not in terms of sets, but in terms of sense. Connect the probability theory with logic. Okay, then we have this presentation here is more a more philosophical analysis made in this way. So we have kind of translations of the axioms of Kolmogorov in terms of sense. And how can make this analysis? We extend the notion of Boolean algebra or the intuition. We see in terms of probabilistic semantics. And here, the semantic, as I talk about classical probability theory, we are based on classical propositional logic. And to certify that this probability theory is very well defined, we prove completeness here. So in classical, we have all this connection very well established. Now, try to extend this kind of analysis by using different of logic. Because we have lots of different logic, why we need to use only position. So I will extend the analysis in terms of sense. I will define the paraconsistent probability theory, and to have a guarantee that this probability theory is well done, we need to extend the probabilistic semantic and change the logic we see and put an paraconsistent logic in his place. And then I prove completeness. Our work is to do this. Now, a question, this is an open problem, is to develop algebraic the part of this study to try to complete this kind of graph. Of course, here we have many possibilities to do here, but this is, I don't have any answer in this direction, okay? Okay, now let's go to the axioms of Kolmogorov, put in terms of sense. Here, we have, I put here lots of formal inconsistencies, but I will show that these axioms is very well connected with the classical axioms of Kolmogorov.
What are the connectives of this logic?
Excuse me?
The connectives of the logic.
Conjunction, disjunction, negation, implication are the classical fragment. Then I will add a new connective.
Bullet?
Yes, like that. Yes. Let me. Here we have non-negativity is the same in axiom of Kolmogorov. Tautologicity, if phi is an axiom or a theorem, phi receives maximum probability. If phi behaves like a bottom particle, then receives minimum probability, 0. Comparison.
What does it mean that?
Huh?
The third proposition, what does it mean? Phi turnstile and nothing on the right.
Phi derives everything to realize this.
You put anything on the right.
Yes. And here, comparison, if psi derives phi, then probability of psi is less than probability of phi, and finite additivity. Now, let's see in terms of possible worlds. Okay, this is very, very easy to see. Thinking in classical okay, you see, like P, Q, 1, 1, 0, 1, 0, 0, then negation, 0, 0, 1, 1, and here is classical, this is a tautology, okay, this is a contradiction, and here is Q. Before, and this is the same for Q. And then here is very clear that the probability of P or not P is 1. All possible words, from specific value 1, and probability of the contradiction is 0. And here, so these two notions is clear. Now, if I think in terms of deduction, take these terms and these terms, they are true only in this simultaneous, only in this line. Okay, so probability of gamma is 1/4. Okay, and probability of Q is 1/2. So comparison is valid. Okay, this is in classical logic.
What is gamma?
Gamma is just a
How is defined the probability of a set?
excuse me.
How is it is defined the probability of a set? So there I only see the probability of sentences.
Yes.
How do we define the probability of a set?
Yes, probability to be the conjunction to be true.
Conjunction.
Okay. Only in this.
That's it.
So we have the comparison. And here we can compute by finite additivity. Have 0. just to have an intuition, in which sense we can attack, put probability in terms of sense. Now, let's show you how it works in paraconsistent logic. Example, LFI1. This is a three-value logic, and we have as a distinct values 1 and half. And take, for example, P and negation 1 half 0. Negation this system in classical values is classical. Negation is change the version here. And if I the disjunction is the maximum, okay? 1 half 1, and conjunction is the minimum. 0, half, and 0. Now we can see that probability of valuation of P belongs to distinct values. This is probability of P. In this case, F is probability. And probability of P case in and probability of a contradiction is not 0. And here we can prove and can see probability of not P by using finite probability. Here we have this and for minus 1. We can reduce the methodology because in LFI1, P or not P is a total. Okay, just to understand how we have logic and probability, how relate this with common concepts. Okay.
So what is the significance of the choice of the capital D? Right, I would get something different if it chose a different D, right?
Distinguished values.
Yeah, but why choosing these and not? I mean, I'm not familiar with this. I mean, for me, it's always, I don't know logics where the choice is kind of
We
really
assume
a parameter. For me, it's always there's a designated like one thing, like true or one. I've not seen or studied logic, so that's not the case. So I would like to understand better the significance of this set of designated.
here is true, and here is not false. That's the idea. And here, in this value is false. True.
But like, I
Not
mean,
false.
if I want more than two truth values, why do I mean, to me, the D, the capital D looks like now I'm forcing everything to be binary again, right? So either D or not D. Why do I do that? I mean, if I want to work with many valued logics, why not just accepting that I have many values? Why making everything two valued again using the D? That's what I don't understand.
It's not exactly like that. Exactly, you have degrees of truthness, if you like.
Yeah,
You can
yeah,
also degree of falseness.
right.
You can have both of them together. It's your choice. It's like you
No,
modeling
why should I choose a D? That's my question.
for what?
Yeah, exactly. For what? Yeah.
So usually what one wants to do is you have those designated values.
Mhm.
Why?
And then you say, okay, those values are acceptable. And then how is the consequence work? The consequence works in this way. If you have a set of formulas and a valuation that makes all of them acceptable, then the conclusion should also be acceptable.
But now you take as, it seems like you take as an assumption that your consequence should be kind of two-way. Why not working with a many-valued consequence relation?
Your valuations are going to assign different values to your system. And then you classify when is going to be the consequence correct. The consequence is going to be correct whenever I value my hypothesis and all of them are acceptable, the consequence is also acceptable.
Okay, but your consequence relation is a relation, right? So it means it's two-way.
Yes.
So why? If I work many-valued anyway, why not working with a many-valued consequence relation?
There are other semantics in which your consequence relation is not one. It's
Yeah.
not value, it's not a relation. But a relation is a probabilistic relation.
No, there's
Yeah,
another-
but so what's the significance or the
You
motivation
can
for doing it like the way you
That's a
described?
famous criticism by Schusko to many-valued logic. You know, in principle, you can prove that any many-valued logic with different truth values has a 0-1 semantics. Okay, then it goes in your into the right direction. Has 0 and
No, I'm saying.
yeah, I mean,
Okay.
0, just because. But the problem is, then your relations become partial. You lose several properties of your relation. And your relation, it goes just one side, not both sides, etc., etc. So in principle, you can reduce many values logic to 0-1. That's Schusko theorem. But then you lose lots of properties. So you choose either you make a truth table, a beautiful truth table, workable, etc., with more value, or you stay with two values, but it's going to be much harder to work. Going to be partial functions, non-truth functional, like modal logic. I mean, the truth value of a composite sentence is not exactly a function of the components, blah, blah, blah. So you lose lots of properties.
Mhm.
But in principle, you can think about that. So like more or less, like you're saying, you divide the world into designated and non-designated. Okay, and then I am in the by value of the world again. But you'll be in a very imprecise two world values, you know. You're going to lose. This is famous debate about Schusko.
Okay.
Yeah.
Um,
I
need
think
to know more about that.
well, Alex is suggesting to generalize further to use a probabilistic consequence relation. We have many valued logic
But that's
and probabilistic consequence.
And imprecise relations in a sense. Right?
Yes, because we identify in algebraic logic is identified with the consequence relation. And that's, I mean, if you want to replace the consequence relation with probabilistic, you would step quite far from algebraic logic as it's classically done.
And the designated values are exactly those which are preserved under consequence.
Yes.
Okay, yeah.
Here we can see that how a contradiction can appear in this context where I'm not really sure about the topic, but it's acceptable. And here I'm completely sure we can say, okay, but this is just to show the motivation. How can use the idea of possible worlds to attribute probability to set. Okay.
You should use it that this is a probability function for the language.
Yes,
But it's not
here.
just for the language, right? Because you're using also the consequence relation in set. So I suppose that you mean a probability function for the logic.
Yes, here is general because I'm not in a particular logic in this presentation. I take only the example.
Yeah. But
Yeah, but
the definition involves one
yes,
particular logic.
here is the language of the LFI1, for example, and here is the deduction of the LFI1. I change the logic. Here I'm presenting in general terms because the same actions are valid for the three.
For example, here, in order to prove that this thing that you suggested here, how to define, in order to prove that this is a probability for this particular logic, you have to prove that all the tautologies are going to be valued 1
Exactly.
and the other things, right?
Exactly. Okay, so in this setting where I choose some logic to put here, I need to prove correctness and completeness. Okay, I will need to prove all these things, but I will skip here. The classical definitions that appears in Kolmogorov's approach, we can translate in terms of sense. For example, the notion of the intersection in end set can be expressed by logical incompatibility. Okay, two sentences I said to be logically compatible when put both together. They are actually as a bottom part of the logic. It realize the system. In this sense, the pair of sense is two classes. So we can prove, for example, these properties, LFI1 and CIA, the three systems can prove these properties. First one is a consequence of the binary sensitivity, probability of distribution is the sum when alpha and beta are logically compatible. Can think that the intersection sense. Then this property is very interesting because we can measure how consistent is a formula. Okay. Note in this example, we have probability of P plus negation of P is for third. Okay, and if I 2 minus 4 third, we have how much is consistent this one. When the formula behaves classic, this sum is 1, okay? And then this seems maximum probability for this one. And here we can measure the contradiction this way. In logical, no. Most of logic, we can define a classical negation for a consistent system, and classical negation behaves as classical, that satisfies the classical probability of negation, and probability of non-consistent alpha is 1 minus probability of consistent. This can be proved in the system by using the axioms of logic. Okay, and then we define a probabilistic entailment. Gamma entails probability phi if only if for all probability function based on the logic that are considered. If probability of the set of gamma is true in this sense here, altogether receives distinguished values in the system, then probability of phi also receive maximum probability. This is, and we can complete this for the system. Okay.
There, when you take the probability of gamma, this gamma doesn't have to be finite.
Yeah.
Yes,
So
yes,
do you mean
yes.
that if the probability of a subset is 1, if the probability of a finite subset is 1?
Yeah, because I have a capacity in the system.
Okay, it's
yeah,
filtering.
yeah.
Is that provably equivalent to saying that for all P gamma is less than P of phi? This is only a special case of that.
No, no, not for all possible distribution. If I have a tautology,
Yeah, but what if I have something less than a tautology? And nevertheless, my probability of phi is at least that. It's
yeah.
at least that much.
So for the completeness, we only consider the maximum probability here. I understand.
Yeah, that's the problem.
Yeah, that's a different, right.
Global and local evaluation. It can be maximally one, equals one. In this case, we are using that, but the general case is one, as you said.
So we prove the completeness in this sense. Now I will talk a little bit about the paraconsistent associated with this kind. Okay. Well, the concept of independence. Two sets are said to be independent if satisfies this probability of conjunction. Very similar. Conditional probability in this set is also the same, just change intersection by conjunction. This is the conjunction of the logical system. Okay. And then now, when I analyze the completeness obtained for probability theory based on this logic, this, all of them, it follows the same actions. We don't need to make any change. And the proof is basically the same, technically speaking. Okay. So the question, which are the difference among probability theories based these logic?
Sorry, guys, can you unmute the speaker?
Is that better?
Let's see, can she say something?
Yes.
Okay, now she's unmuted. Thank you.
It was us, don't worry.
No.
It's fine.
All good.
It's fine.
When I'm in this logic, I have only one version of the total probability theory. So when I work in this article, can see where is the difference. This question is very. This question is important. We can see the difference when we work with this logic because different versions can be applied. In case of LFI1, I have two different ones. Okay, but when I talk about total probability theory, we need the concept of partition. Okay, we have we separate the sample space in different parts. Each one has intersection 0 between them and has no overlap. I need to generalize this notion, and I propose a cleavage. Cleavage. A cleavage is a family of propositions and is exhaustive if the disjunction of this proposition is a tautology, and is exclusive when they are pairwise logically incompatible. I have this here, classical. Okay, the disjunction is the tautology, the union is the sample space, the intersection is empty. But when I'm consistent logic, I have contradiction. And then depends the logic will vary. Okay, in case of LFI1, this part is valid, but this is not. We have intersection between. So the total probability theory can be obtained, for example, in LFI1 in two different versions. I will show only these two versions. Okay, and here I will think in terms of information about alpha to make sense to accept the overlap of the two sets. Let alpha be a sentence where the information about the alpha is excessive. Let omega be the sample space divided in terms of information about alpha, and let be a sentence in omega. Then probability of beta can be obtained in this way. Look, this is classical, and we subtracted this part, which I have the intersection. This is just there's and the second version is in this way. In terms of information, what it means, I can see that I can organize or separate the information in at least in two different ways here. Information about alpha, information about creation of alpha, and the information that has contradiction, this part. Or I can separate good information that are consistent and bad information that has inconsistency. Separate in two groups, and then we'll have two versions of theorem. Okay, just to visualize in a graph. Of course, here beta could be inconsistent too. I didn't consider because I had no space to put here. Okay, but this is the organization of the data that I can do. And now, as I have two different versions of total probability theorem, of course, I will have two different versions of Bayes theorem.
So can I think of black circle alpha as the gap? I think you called it last time.
This is consistent information about the alpha, and this part is inconsistent information about the alpha.
Can be the gap or the overlapping.
No. Here
in this logic.
In this logic, LFI1, I only admit excessive information.
Then the black one means overlapping.
Yes, overlapping.
In this logic.
Yes, but the other logic, the last weekend, we have 6 possibilities. Okay, and then we can have different versions of the Bayes theorem, because here the denominator I have the total probability here. Probability of alpha given beta is the reverse probability multiplied by alpha divided by probability of beta. And then we have the first version based on the first version of the total probability theorem, and I have the second version. Okay, now we can apply this in problems. So just to summarize, in this logic, we have only one version of this probability, total probability theorem, version 1. In LFI1, we have 2, and in logic of evidence and truths, we have 6 versions, one for each scenarios that I can obtain, because we have lots of possibilities. I have excesses of information, overlap of information, I have a gap of information, and then I can combine all situations here in these 6 scenarios. For each one, we can prove different versions
Is
of
there
it.
a procedure or schema for combining all versions if there are more than one total probability into a single version, but they are mutually exclusive?
I didn't hear you say. We didn't hear.
Let me think about. I'll ask after. Yeah,
No,
I'll think about more about
say
it.
again.
Well, I was gonna say, is there a way to combine if there's more than one version of probability,
Yes.
total probability?
Uh,
Is there a way to bring them all together into a single schema?
Bring it all together. I don't know. Perhaps
know.
not.
But
Perhaps not.
the idea here is that you can have freedom to organize or to see the problem as you like, and it offers for you different ways to work. Like we do in statistics, we organize the data way, we have one kind of analysis, another. That's the idea. Now I will finish here with an example. Okay, I will apply this probability theorem in a paraconsistent Bayesian span filter. A Bayesian span filter analyzes suspicious characteristics in the body of messages, like headers, code, colors, words, expressions, etc. And some words are suspicious, but some are just dubious. For example, sex, buy, cash, all things are suspicious words. But free now, just
Buy now.
Yeah.
Everything for free.
Free groups, free algebras.
That's very dubious.
Only dubious.
That's very dubious.
Yeah.
Very, very dubious.
Now, suppose that the historical
Is this free beer or free group?
2 different protection systems. For example, Gmail, filters, and spam assassin filters. The first one, the Gmail, gives the amount of messages is spam, given this information, 30%. The other one gives probability of not spam, message, is 85%.
I think that's a very low probability of spam.
Yeah.
30%?
It's what the beginning of the system.
Yeah,
Now,
it's approaching 100.
suppose for a given word or characteristic, we have this probability of W given that message is spam. I compute this as the proportion of spam containing W, contains such characteristic. Also here is the proportion of ham documents contain this characteristic. Now, here I have contradictions. span and elongation of span is 15%, and we can add these informations. Probability of having such a characteristic, since given that is a span, it's 9%. Have such a characteristic, even it's not a span, 20%. And here, when I do the contradictory part, we have only 1%. This is just an example. I can change these numbers, not a problem. Okay. Now, the question that you can do is, what is the probability that an email, given that the email contains the suspicious word? We can make the question in the reverse way. Now, I just organized the data of the problem in this scheme. Okay, to prove the total probability, we consider each possibility of W, and then I will compute applies the base theorem in the version 1, because I divide the data in 3 different sets here. So we can get this number. Okay, plug in the values. That probability of is span given has such a characteristic, 62%. Now, I want to compare these results with classical results. And then I will eliminate the contradiction, just to think. Well, I can this is in excess in this part, and 85% by 70%, or this part, or you can check. Okay, make the 3 scenarios. We have that the probability of S given W is 6% in this case, where when the proportion of span is great, when proportion is down, this number, in the middle I have, look, our result is it's not crazy.
Significant.
Yes, it's very significant results. So, just to paraconsistent probability is quite rational in this setting. It provides reasonable results work directly from contradictory data. Bayes' theorem in a paraconsistent set can be seen as a promising tool for make decisions under error, and paraconsistent probability can be viewed philosophically as a genuinely new tool for reason. That's what I just help to okay.
Thank you.
So extending your last example, right? So whenever we do data analysis, we spend a lot of time cleaning and preparing the data, right? And that's always a process which is kind of looks a bit arbitrary and ad hoc and can have significant impact on the results we get at the end. So could your method kind of be used more generally to not having to clean the data? You can just take data as it is and still get a reasonable analysis.
Yeah, that's the idea.
Right. Okay, that's the idea.
Spend time in data.
So
much cheaper and faster, right? Much cheaper and faster.
But then also we need to experimentally evaluate is, right, with lots of examples.
Yeah,
Well, there's also, it's not just clean, it's not just faster and all that, but it actually might be more informative because
That's what I.
as soon as you clean data, you've actually you've imposed
Mhm.
information that wasn't there. So you can now start hallucinating based on what you've, based on cleaning, right? So this is a guard against importing things into your data that aren't there.
for instance, I think one important application would be in election polls.
Oh,
Election,
yeah.
yeah, because there when you have contradiction, you cannot just clean it because it has a significance, very significance, political importance in this contradiction, right? So real analysts should be taking attention to that. We proposed in Brazil before the elections to use this in some election, some companies that do this kind of, and they said, no, it's too much complication for the moment, don't do that now, please wait. I wrote to a newspaper asking.
And you could make your own data analysis.
We could do our big company.
To them that you're better, that you make the better
predictions.
Yeah,
we could open our own company. Yes, like
yeah. And this Nate Silver person.
Nate Silver, for instance.
Got famous with
Nate Silver should pay attention to that. Make some mistakes.
Yeah. He also made some mistakes.
Yeah.
Yeah, that's very nice.
Questions?
It was a surprising finale because it was all logic and mathematics, and then at the end it turned out to be like potentially very interesting with respect to very concrete kind of data analysis.
Yeah.
So I'm very interested in whether you really can bridge the gap. That would be really super cool.
One thing that we don't know, for instance, is how this accuracy of the results now depends on the degree of contradictions. If it has too much, like let's say 35% of contradictions, perhaps it's not going to work. So there should be some boundaries that have to be explored. I mean, mathematically and by using tools of statistics, not probability only. Like distributions this kind of statistical distribution that I don't know much about, but perhaps you guys know, and try to apply that for massive data, big data, whatever. So there's lots of work to be done. We are very glad that you are liking. Maybe you can do something together. So we came here for that.
Yeah.
We teach data science, and a lot of our students are interested in data science. So potentially to create a research project with real data and let the students work on it.
Yeah, this kind could be applied in Bayesian networks.
Yeah.
Because we have a conditional probability based on different kind of logic.
Yeah, the definition of the probability logic, you use all the possible distributions.
Yeah.
I was thinking whether this could be done with only one distribution or the finite subset distributions. Some distributions that are specially fitted. Or you need all distributions, you need to consider all distributions.
I don't know.
Maybe. I mean, distribution like a Poisson, this kind of thing.
Yeah, well, for example, you're saying that gamma implies phi, all p, if something, you could do that with only one, if you want.
Yeah.
Or with all distribution of this kind. I don't know.
We don't know. It's just quite new ideas.
Yeah, the tautology, for example, is not impacted for any distribution.
Yeah.
That's
so this
the
doesn't
idea.
mean so no. Doesn't matter if you consider all of them or only one, the tautologies are going to be the same.
Yes.
It doesn't affect those, right?
Yes.
So I was wondering if, because, well, it's a significant effort to consider all the possible distributions. If there is for some particular logics, you could consider only this kind of distributions, then things could be simplified.
Possible.
That might raise a related question. So your analysis has to do with reasoning, I would say, with probabilities, but not really about probabilities. So you could also think in computer science, people talk about probabilistic power domain constructions. So you have some internal logic of a system. But then you can also consider a logic in which the propositions are things like the probability of this is above 1/2 or below 1/2 and so on. And that's a logic about probability rather than a logic with probability. And I wonder if there's any room for thinking about that, because that would allow you to address these kinds of questions. Then you could reason about the distributions.
Yeah, yeah.
Yeah.
I think, yes, included there is an area which called possibility theory.
Yeah.
Like possibilistic theory or possibility theory,
Yeah.
where you sort of work with imprecise probabilities or bounded probabilities somehow, then takes you to that area you are mentioning. So yeah, we have done some work on that, but this is just brand new. I mean, nobody's working on that. Very few people that I know.
So what about like predicate extensions of this?
Predicate logic, I mean,
Oh, predicate. Oh, I didn't consider yet predicate logic.
yeah, it's more complicated.
Yeah,
Yeah, I'm also not sure if it's so clear what it would be.
maybe.
Yeah, then you need
Yeah,
some.
Other
Continuous
Continuous
function, right?
functions, yes.
Continuous, not that discrete like that.
Yeah.
Continuous and with other area.
It's
One of the problems is, in my opinion, there's no something like algebra of sets or how do you call this algebra that they use in
Sigma
algebra. Yeah.
algebras.
There's nothing like
Yeah.
sigma algebra yet.
Yeah.
For some logics, we're trying to develop a kind of algebrization that could take us to something closer to a sigma algebra. And then we could, as in classical logic, you work simultaneously with events and statements.
Yep.
Not anything done for the moment.
Yeah, in my intention here in Chapman is to analyze the behavior of the implication in the system and try to analyze the behavior in a paraconsistent logic, because we have
You mean
lots of-
conditionals in
yeah,
general? Yeah.
because we cannot if I probability of A given B, this is a very complicated question, and we have used triviality. But if I work with a three-valued three-valued logic, we can derive this as a theorem, and then which impact this have now. I need to change the logic, of course, and I'm trying to analyze this because here we cannot make this. This problem. So to make some restriction, then we try to just think about it.
Like, why can't we do that? Why can't we do the nested implication?
Well, that's
Because when I
Because you don't have a Cartesian closed category.
when I compute, this is when I think in classical terms. Adam's works, it is problematic because it's very complicated, and then I have a problem because when I talk about undeterminedness, okay, the implication is true, and it's false. And this is strange. terms of betting, how can I manage that in this sense when the antecedent is used? This is very complicated. And then to avoid this kind of thing, they are using them once this implication does not do that to avoid problems. But in tree-value logic, we can show that it's possible. Because
Yes.
and you can, but this is what I'm looking at. This does not.
This is your research plan, right?
Yes, yes.
You have to finish it.
No, I'm just starting to think about it.
So the connectives are, as I'm teaching my students, truth functional, but are the connectives also probability function? I mean, is that part of the problem here, or are the probabilities always preserved
But the bound preserves.
by the connective?
Yeah, preserves. It's not connected with the function.
Okay, sorry.
This is just to, because this is very intuitive, this identity.
Yeah.
Be notes to be as the classical logic. This is a problem. This trivializes the notion of probability. Okay, so classical logic has lots of equivalence that destroy it. Other logics, we can restore this. We try to apply this. I don't know how to do it. I see.
Thank you very much.
Thank you. Thank you, speaker again.
Okay,
Thank you.
Yeah, because I guess you have